few MCQs, that's a multiple choice questions based on analog integrated circuits. Okay, myself, you all know I'm Dr. Sareen, and I'll be dealing the master like multiple choice questions which are most important as a part of the university question papers. So let us now enter into this lecture. Now let us see another few sets of MCQs on this operational amplifiers here. The first one here is, which is not the internal circuit of an operational amplifier? Which is not the internal circuit of operational amplifier? The first one is differential amplifier, second one is level translator, third one is output driver, and the fourth one is clamper. So I hope you all remember the internal circuit of your operational amplifier or the block diagram, how it has been written. So here first one, our operational amplifier will be having input stage. The first one is an input stage, and this input stage is being designed with the help of a differential amplifier. It's a DA. DA is used to define the input stage. So input stage first will be an input stage. Then after the input stage, you will be having a gain stage. You'll be having a amplification stage, or else we call it as a gain stage, where the gain of your first stage will be amplified over here. So it is called as a gain stage. And after that, you will be going for your level translator or level shifter. You'll be having a level translator or level shifter. It's a fourth one. And the next one will be output stage. The next one will be output stage. The fourth one will be the final stage of your operational amplifier will be, that is nothing else but it's a output stage. First one is an input stage. The second one is a gain stage. And the third one is level translator. Fourth one is an output stage. In the output stage, we have studied that here the output stage will be designed with the help of a push-pull symmetrical amplifiers. It's a push-pull amplifier will be used for designing your output stage. So now you can, from this particular diagram we have drawn, you can tell what is the correct answer. Which of this is not the internal circuit of an operational amplifier?
Clamper.
Clamper is the correct answer. Why? Because you do not have the clamper over here. You do not have the clamper here. You are having an input stage. That's a differential amplifier is the first one. Second one, you are having level translator is given. That is nothing else but level shifter. The other name for the level translator is a level shifter. So you are having that level translator. And the third one is a output driver. Output driver is nothing else but your output stage. Output stage. Why it is called as a driver? Because it has to drive the next whatever the circuit is being connected over here. And only the left out one is a clamper. So your clamper is not the correct one. You can see the answer is what? D. D is the correct answer, which is not the part of your operational amplifier. So see the explanation. Clamper is an external circuit which is connected to the output of an operational amplifier, which clamps the output to decide DC's level. What does a clamper does? It will clamp the output to a desired DC level. So ultimately, as per this question, your answer is D. That's a clamper is not the part of this internal module or internal circuitry of your operational amplifier. Second one, the purpose of level shifter. The second one is the purpose of level shifter in operational amplifier internal circuit is to. What does a level shifter does? So let us see now. Options are adjust DC voltage, increase impedance, provide high gain, decrease input resistance. Among this one, the answer will be A. That is to adjust the DC voltage. It has to adjust the DC voltage. Let us see what's the explanation. The explanation, it tells that the gain stage in op-amp are direct coupled. Gain stages in the op-amps are direct coupled. Because of that one, level shifter is used for adjusting the DC levels. What is the main functionality of a DC level shifter? See, So try to remember this question such a way that why the level shifter is being used. The level shifter is used to adjust the DC levels. That's the important one. Level shifter is used for adjusting the DC levels. That's the most important one. Try to remember it. It is used to adjust the DC levels. Third one, how a symmetrical swing is obtained. How a symmetrical swing is obtained at output of op-amp. What is the options? Options are providing amplifier with a negative power supply. Second one, providing an amplifier with a positive power supply. The third one, it is providing an amplifier with a positive and negative voltages. Fourth one is none of the mentioned. Among this one, actually the answer will be the third one, that is providing the amplifier. Why does we use the symmetrical swing? The symmetrical swing is obtained at the output because in order to provide both the positive and negative voltages. In order to provide both the positive and negative voltages. See here now, you will be having both the, if you talk about an output of your op-amp, the output of an op-amp will be having both the positive and negative cycles. So it will be having both the swings. The swings will be there. Op-amp, I'm drawing the circuitry of the diagram of your non-inverting amplifier output. It will be having both the plus, that's a positive cycle, and also it will be having the negative cycle. This is what we are talking about, the swing. To what level the amplitude of this voltage is going, to what level the amplitude of this particular signal is going. This will become the positive swing and this is going to become the negative swing. It depends upon the voltage supply which you are given. We have studied in the previous lectures that the swing of your voltage, the swing of your circuit depends upon your VCC, that's the power supply which is given to it. Means what? If you have supplied 12 volts, if you have supplied at 12 volts, your maximum output voltage can go up to 12 volts only. It cannot go beyond 12 volts. But in fact, that's whatever I told now it is. If you are supplied at 12 volts, your output can go up to only 12 volts. It will not go beyond 12 volts. That is the ideal condition. But when I speak practically, what happens in the practical scenario? The op-amp is going to enter into its saturation stage at one particular voltage. Means what? As per the research has been conducted, the swing of your output voltage can go up to only the 90% of the power supply which is given to it. Means if I have supplied some 12 volts, if I have supplied a 12 volts as an input signal, power supply, your output can go only up to hardly 10.5 or 10.8 volts. Beyond that one, your output will not go high. Means beyond that one, your output is going to become saturated. Even though you increase your input voltage, your output will be saturated. Now let us see the explanation for this one. Why your answer is C? Why the answer for this one C is correct? So see now. Explanation. For example, consider a single voltage supply plus 15 volts. During the positive half cycle, the output will be plus 5 and minus 10 volts during the negative half cycle. Okay, they have taken one scenario here where the power supply is plus 15 volts and they have given that for during the positive cycle, what is this peak value of this one? It is mentioned that the peak value is taken as plus 5 volts. They have taken one example as peak value is equal to plus 5 volts, and here the peak value of the second one, negative cycle, it is taken as minus 10 volts. In this example, minus 10 volts. Therefore, the maximum peak to peak output swing is equal to minus 5 minus 10, that is equal to minus 15. It is going to be minus 15, which is an asymmetrical swing, which is not symmetrical. Why? Because there we have taken the positive 5, it is coming here minus 15, so it's not symmetrical, it's going to be asymmetrical, but ultimately you are going to get a swing of the voltage. It is not going beyond that one, it's going to be exactly, which is a practical ideal case. So to get a symmetrical swing, both the positive and negative supply voltage with a bias point fixed suitably is required. So you are supposed to have, if you want to get a symmetrical swing, means what? If you are given a positive 15, ultimately when you see the combination of this one, it has to be plus 15 only. It has to be a symmetrical swing. So in order to get the symmetrical swing, what we are supposed to do? Both this positive supply and negative supply should be biased at a fixed point which is suitable for this operation. So this is regarding this one now. Ultimately, you are supposed to keep in your mind how a symmetrical swing is obtained at the output of op-amp. The symmetrical swing is always calculated by taking the positive and negative voltage into consideration. Symmetrical swing will always takes the combination of both the positive. It is obtained by what? Providing both the output, providing the amplifier with a positive and negative voltage. So your option here, C is the correct one. C is the correct option. Fourth one. Here in the fourth one, what is the purpose of differential amplifier stage in internal circuitry of op-amp? What is the purpose of differential amplifier stage in the internal circuitry of op-amp? So they are asking, just now I have drawn it, the internal circuitry. What does a differential amplifier does? We know that what your differential amplifier does. Differential amplifier is nothing else but it is going to find the difference of the input voltages. It is going to find the difference of the input voltage, and that difference is going to be amplified. Means what? You're giving in the differential amplifier, it is going to cancel the common mode signals. Ultimately, the common mode signals are nothing else but the noisy signals. That noisy signals are being cancelled over here. We all know that common mode signal is what? It's a noisy signal. That noise signals are being cancelled. So that's why your option is, fourth option is the correct one. So explanation C here now. Any undesired noise which is common to both the inputs is suppressed by differential amplifier. That's why it is called a differential amplifier. It will take the difference of the inputs. It is not going to amplify both the inputs as you supply. It is going to take the difference of the two inputs, and that difference is been amplified. Means what it's actually doing? It is cancelling all the noisy signals, and the difference itself is magnified or amplified. So your answer D is the correct one here. So it will cancel the noisy signals. That the other name for the noisy signal is common mode signal. So the answer D is correct one. Fifth one. Which one of the following is not preferred for input stage op-amp? Which one of the following is not preferred for input stage op-amp? Let us see what the options are here. Here options are dual input balanced output, differential input single-ended output, cascaded DC amplifier, single input differential output. See here now, in the operational amplifier we have seen all these three configurations. We have seen the configuration of differential input balanced output. We have seen this configuration of differential input signal with a single-ended output. We have seen single input differential output. So only the odd one out of this one will be the cascaded DC amplifier. So the answer C is the correct one. Cascaded DC amplifier is the correct one. Why it is not preferred for the input stage of an op-amp? Let us study why it is not preferred here. Because the DC amplifier or the cascaded DC amplifier will suffer from major problem of drift of operating point. It will be having a drifting problem at the operating point due to temperature dependency of the transistors. The transistors, we all know, it depends upon the temperature, and effect of temperature will always degrade the performance of a any kind of circuit, let it be an amplifier or any kind of circuit. But coming to the cascaded DC amplifier, the disadvantage of DC amplifier is what? It is having a major disadvantage, that is, it is having a problem of drift at the operating point. At the operating point, it is having a problem of drift, thermal drift. Actually, we call it as a thermal drift. So it is having a problem of thermal drift. So because of that thermal drift, it cannot be used for at the input of the op-amp. So option C is the correct one. Sixth one. What will be the emitter current in a differential amplifier? What will be the emitter current in a differential amplifier where both the transistors are biased and matched? What will be the emitter current in a differential amplifier where both the transistors are biased and matched? Assume the current to be IQ. Assume the current to be IQ. Here, excuse me. Let me skip this one and I'll explain you in the next class. Why? Because options I have not given here. Let me go for this next one. Okay, see now. At what condition differential amplifier functions as a switch? At what condition differential amplifier is functioning as a switch? Here, switching is nothing else but it has to act as a turn on and turn off just like a transistor. So let us see what's the correct option. The option correct is here as per the slide. A, first one is the correct option. Let us see why the first option is correct one here. Because your VD has to be always greater than 4 times of the threshold voltage. It has to be 4 times of the threshold voltage. So therefore, the output voltage is calculated as VO1 for VD is greater than 4 VT. The output voltage are VO1 equal to VCC and VO2 equal to VCC minus alpha F into IQ into RC. This formula we have studied. Therefore, a transistor Q1 will be on and Q2 will be off. Depending upon these conditions, whenever the Vout is equal to VCC, here at this case your transistor Q1 is going to be on. In the differential amplifier, I have just drawn the diagram here. Your transistor Q1 will be on this is your Q1, your transistor Q1 and transistor Q2 where you can see all the terminals. So these are the terminals, base, collector and emitter. So for the condition VD is greater than V4 VT, excuse me, VD is greater than 4 VT, the output voltage or VO1 is equal to VCC and output voltage 2 is equal to excuse me. For VD is greater than 4 VT, the output voltage or VO1 that is equal to VCC, and for the second output voltage we are talking over here. This one here you will be having the two collectors, VO2. This is your VO1 which is taken in between that resistor. You will be having one resistor here like this, and this will be your first one, and this is another resistor R2, and VO1 is nothing else but your voltage across the C1 collector 1, and VO2 is the voltage across the collector 2. So this is your circuit which they are talking here now. So now your VO1 is equal to VCC and VO2 is equal to VCC minus alpha F IQ into RC. Therefore, because of this one, your Q1 will be turned on. It is the Q1 is turned on and Q2 is going to be off. Q2 is going to be off. Whenever the Q1 is turned on, the only one transistor is going to be turned on. And in the second case, what's the second case? We have taken up to now first case. What's the first case? Whenever the VD is greater than 4 VT. What's the second case now? Whenever the VD is this one. So see now, whenever the VD is now greater than minus 4 VT. Whenever this one, both the transistors Q1 and Q2 will be on. So because of this reason, the first condition will be the correct answer. Answer A is the correct one here. Next one. Change in value of a common mode input signal in differential pair amplifier makes. If the values of the common mode input signal in differential amplifier is being changed, then what will be the correct answer? So see now. the change in value of a common mode input signal of a differential pair. Differential pair amplifier means what we are doing here. We are giving, it's a differential amplifier where you are giving the two different voltages V1 and V2. It's the same circuit here which we have talked here, but you will be having the two voltages. Two different signals have been given. This is V1 and V2, which are different in many ways. So this is V1 and V2. So it's a common mode signal. Okay, change in values of a common mode signal here for a differential pair amplifier makes. What does it do? It will always see the options. Change in voltage across the collector, slight change in voltage across a collector voltage decreases to 0, none of them mentioned. See, whenever you are changing the input signals, so ultimately what happens? The voltage across the collector is also being changed. Whenever the input signals have been changed, so definitely you are going to get a different collector voltage. It is not, we are not biasing the circuit with the same voltage. Here in this case, whatever the problem we are discussing right now, it is mentioned that your V2 is not equal to V1. Your V2 is not equal to V1 over here. Your V2 is not equal to V1 means what? Ultimately, it is a differential amplifier with two different inputs. If it is a differential amplifier with two different inputs, so ultimately you are going to get a difference in the collector. So the collector is also going to change ultimately. Whenever the inputs are same, whenever V1 is equal to V2, what happens? The output will be 0. Whenever the V1 equal to V2, output is going to become 0. Collector voltage is going to become 0. But here in my case, what is the case? Your V1 is not equal to V2. So that's why the correct option is A. That's A is the correct option. There will be a change in the voltage across the collector. See now, explanation. In differential amplifier, due to symmetry, both the transistors are biased and matched. Therefore, voltage at each collector will be same. Okay. In the differential amplifier, whenever they have got both the transistors are biased, the output voltage will be same. But the condition is given is what? You are changing the input signals now. Because you are changing the input signal, ultimately the collector voltage also changes. Collector voltage also changes. So that's why your option A is the correct one here. Have understood? Is it clear?
Yes, sir.
Yeah, now this is one numerical kind of question. I hope you are familiar with the numericals and the formula. So find the collector current IC2 given the input voltages are V1 equal to 2.078 volts and V2 equal to 2.06 volts and the total current, that's IQ, is equal to 2.4 milliampere. Assume the alpha value is equal to 1. This is a circuitry which is given to us. You are having the two inputs. Where is my pencil? Okay. You're having the two inputs V1 and V2 of the transistors Q1 and Q2. RE is given over here, emitter resistance, and then it is been having the two collector resistors RC with two different currents, that IC1 and IC2 output currents. So now we are supposed to, with all these values which are given to us, V1 is given as this, V1 value is given as 2.07, V2 is given as 2.06, the total current IQ, the total current is equal to 2.4 milliamperes. You should find out which is the correct option. Here, as per my calculations, the correct option is A, that is 0.8 milliamperes. Let us see how it is A. Collector current formula, we know it, that is IC2 equal to alpha F into IQ divided by 1 plus E to the power of V, and this is a formula which you have used there, E to the power of VD divided by VT, and the VT is nothing else but volts, equivalent of the temperature, that is equal to 25 volts. And if we substitute here VD, we know what is the VD. It's the difference of the two input signal, that's the difference voltage, V1 minus V2. So here we are having VD here in this formula, that's why we are taking the VD. That's V1 minus V2 equal to 2.078 volts minus 2.06, that we get across 0.018 volts. Let it be my equation number 1. Now substitute the equation 1. Substituting equation 1, what do you get here? Vd upon Vt. Vt is already, we know what is it. It's a voltage equivalent of temperature. It will be, it's a default value or the researched defined value, that's 25 millivolt. So Vt is equal to 25 millivolt. Substitute here in order to get this equation. It is Vd upon EMA. So see here, it is e to the power of Vd upon Vt. So in order to get this particular fractional term, we are doing this one. Vd upon Vt. You can see now it's actually because of some pasting problem. It has got some change in its values terms. It is e to the power of this. This should be like e to the power of this value. It is e to the power of Vd upon Vt. So we need to find out the fractional term of this one. That's Vd upon Vt is equal to 0.018 volts divided by 25 millivolts. You get the value is equal to 0.72 volts. Now you substitute this value in this equation. When you substitute this value in the equation, you get IC2 equal to alpha. What is that alpha? Alpha value is already given to us. Alpha value is equal to 1, it is given. That is 1 into, what is the value of IQ? IQ is given to us. IQ is equal to 2.4 milliamperes. 2.4 milliamperes divided by 1 plus e to the power of this value. E to the power of how much? 0.72. When you substitute this value, you are going to get the value of IC2 is equal to 0.8 milliamperes. IC2 is equal to 0.8 milliamperes. So ultimately, your answer A is the correct one. Answer A is the correct one. So next one. A differential amplifier has a transistor with B naught, that's with beta naught is equal to 100, is biased at ICQ. A differential amplifier has a transistor with beta naught is equal to 100, is biased at ICQ, is equal to 0.48 milliamperes. Determine the value of CMRR, common mode rejection ratio, and ACM, common mode gain. You are supposed to find out ACM, common mode gain, if RE is equal to 7.89 kilo ohms and RC equal to 5 kilo ohms. Options are given to us. We are supposed to find it out with the value of CMRR. So now let us see here now. See here now, substitute the formula. You all know the formula for this one. Differential mode gain is equal to ADM is equal to minus of GM. What is GM here? The GM is the transconductance. GM is the transconductance into RC. This formula we have studied. ADM is equal to minus GM into RC, and common mode gain is given as ACM. That ACM equal to minus of GM into RC divided by 1 plus 2 times of GM into RE. So this formula we have studied, provided for beta naught is greater than 1. Anyway, the beta naught value is given as 100 to us. So the condition is also satisfied. Now let us substitute the values. GM, we know the what's the value, what's the formula for the GM. See here, what is the GM? GM is called as a transconductance amplifier. We have studied in some of the circuits that it is voltage to current converters. Is it fine? Transconductance circuit we have studied. It's a voltage to current V to I converter and I to V converters. So here voltage is given as an input, output will be current. So if you substitute that value here, I'll write here voltage is equal to GM excuse me, it's not voltage equal to this one. It has to be your current, output current. It has to be output current. That is output current is equal to, it has to be output current equal to GM times of input voltage. So this is your formula. Why? Because we are trying to give the voltage as an input. The input will be voltage and the output is going to be current. That is nothing else but the voltage to current converters. So in the voltage to current converters, we have studied this formula. The output current equal to GM times of Vin. From this formula only, we can directly write from this formula what is GM here. GM is equal to the formula of GM equal to I upon V. We are going to get the formula of GM equal to I upon V. That is the current, output current upon input voltage. It is output current upon input voltage. So see here now, substituting the values, GM is equal to ICQ upon VT. So it is I upon V. That's what I told you. GM equal to I upon V. So don't get confused here how you got this GM equal to I upon V. We have studied it in voltage to current converters. GM equal to I upon V, that is ICQ upon VT. We know VT is nothing else but the temperature equivalent voltage. So that is 25 milliamperes. It's a default value, and ICQ is given to us. What is ICQ? ICQ is equal to 0.48 milliampere. Substitute this value, you are going to get the GM. It's a transconductance. See here, GM is what? It's a transconductance. Transconductance means what? It is an opposite to the conductance. It's an opposite to the conductance. So your unit for the transconductance will be 1 upon ohm. Or else simply I can say it is a mho. The unit for the conductor. So see here now. Excuse me. It's a transconductance. Transconductance means what? It is ampere upon volt. It is an ampere. The unit will be ampere upon volt. We know that the formula is R is equal to V upon I. That's a Ohm's law. Formula is R equal to V upon I. V upon I, that's a Ohm's law. Volts upon ampere. If I try to write down the units over here, the units will be volts upon ampere. The volts upon ampere is nothing else but we can write it as the unit of this one will be, the unit for this resistance will be ohm. So now it is what? It is I upon V. I upon V means what? It is opposite to your resistance. So the unit for this one will be mho. Opposite. It is ohm. You write it as ohm over here. OHM. Here for this one you write it as mho in a reverse manner. MHO. This mho. So that's why you can see now. The unit of this one is given as this one. Mho to the power of minus 1. Mho to the power of minus 1. And we have just now we have found out what is GM. GM is equal to 19.2 into 10 power minus 3 upon mho. 1 ohm to the power of minus 1. So it is in the denominator. So we have taken this minus 1. And ADM. Find out the ADM. ADM is equal to, formula of ADM is what? Gain is equal to GM times of minus GM times of RC. Substitute the value of GM. Just now we have found out RC is given to us. RC is given to us 5 kilo ohms. And ACM formula, you know, just now we have studied here. ACM, this formula. Write down the formula and substitute all the given values here and do some simplification. When you do the simplification, you are going to get ACM equal to minus 0.3158. When you do this one, you will be getting the value of CMRR. What is CMRR? CMRR formula, okay, I forgot to write down the formula of CMRR here. Excuse me, I'm facing some problem with the mouse. CMRR, the formula for the CMRR, you can note it down. It is equal to ADM, that's a differential gain. It's a differential gain, that's a AD upon common mode gain. The formula for the CMRR will be differential gain upon common mode gain. That's why I have written here it is minus 96. What is minus 96? It is a differential gain. And what is minus 0.318? It's a common mode gain. So it is differential gain upon common mode gain. When you do this simplification, you are going to get your common CMRR is equal to 303.976, and we have got the CMRR. You are supposed to find out what is that particular CMRR in terms of dB. So see now, we have got the CMRR, but it is not all the options have been given here in dB. So how to convert this CMRR into dB? You are supposed to apply the log. I have told you the CMRR in dB will be 20 log of that particular CMRR is a formula. In order to convert into dB, it is a 20 log of particular CMRR. So it will be 20 log of 303.976. It is equal to 49.68, 49.65. It's 49.65. So your option B will be the correct one. Your option B is the correct one. So this is a way how we are supposed to find out CMRRs if this kind of numericals have been asked. Always keep in your mind your analog integrated circuit or linear integrated circuit is a kind of paper where numericals are being asked rather than the theory part. If a theory kind of MCQs has been asked, it's well and good, but try to prepare even the MCQs from the point of numericals also. Okay, thank you for this one. I hope you have understood these particular concepts.